The following video will present application-level autonomic hardware to predict and preempt software attacks on industrial control systems. Presented by Sam Calabrese, CS 6263, fall of 2019. Authors are Lee W. Lerner, Zane R. Franklin, William T. Bauman, Cameron D. Patterson. The paper was presented 2014 at the 44th Annual IEEE IFPI International Conference on Dependable Systems and Networks. The paper URL is listed there in the slide. The overview of the paper: a solution to resist software reconfiguration attacks. In essence, what this means is the authors are presenting a solution to resist any attempt to reconfigure a PLC in real time. They use prediction to preview the primary controller actions if the physical process becomes unstable and allow a backup copy controller to be substituted. This is achieved by using application-specific configurable hardware to monitor and potentially override software operations in real time. They use an FPGA to build the prediction unit and backup controller. The regular controller is running on an ARM processor. So to introduce some security issues that are present today. Vulnerabilities exist in all control systems, with some having potential catastrophic consequences if compromised. Consider oil and gas refineries, nuclear power plants, our nation's electrical system. Those get compromised, it could be catastrophic, some of the situations that could occur that would happen. So this paper is trying to present an alternative way of having security on PLCs without relying on operating system or network-related authority and authentication systems. So many industrial systems are engineered for reliability and performance and not necessarily security. This is obviously, to make sure that the systems are always up and running 24 hours a day, 7 days a week. They have to be online. They can't have an instance where these systems are offline or shut down or anything like that. Security is relied on, obviously, physical access to monitoring stations and controlling stations for these PLC units that are out there in the field. So mostly attacks will focus on the network protocol and supervisory platform exploits. These consist of zero-day exploits, and a lot of these are actually available to purchase for brokerage houses on the dark web directly from hackers, if you know where to go and find them. So attackers are more motivated by ideology than by financial rewards, and they have large resources available. So consider nation states that are terrorist based. They don't care about the money aspect of hacking into systems and destroying them. They want to disable infrastructure or for whatever political means or ideas that they want. I also think of very aggressive military-based nations that are looking to, create instability in other nations. So they are not looking for financial reward, as opposed to hackers who are interested in, immediate financial gains from credit card systems or your checking account or whatever. So this paper focuses on the worst case scenario, where the SCADA networks have been penetrated and the PLCs have been reprogrammed. So this is they're already way deep into the system, and think of sort of like Stuxnet, what Stuxnet did. Was able to reprogram the PLC, and the engineers and operators had no idea this was going on because it was recording or actually giving normal operation variables back to their HMIs, so they had no idea what was going on until it was already too late. So their proposed solution is called TESIP, and again, they don't rely on trust in any software layer on any ICS node. So again, they're not worrying about, hey, whatever authentication, authorization has been done prior to gaining access to this PLC. They're going to assume that if you've gotten that far, obviously the system's already been compromised. Let's see if we can handle it at the level of the PLC. So TESIP stands for Trust Enhancement of Critical Embedded Processes. This method is ensuring process stability in a way that does not rely on trust in any software layer on any ICS node. Our isolation is achieved using high-level synthesis, HLS, targeting configurable hardware on commercial system-on-chip IC used to implement the PLC's microcontroller. If you've ever heard of FPGAs, this is what they're using. And FPGAs is a really cool technology that allows you to reprogram chips on the fly. So even after they're manufactured, you can go out in the field, physically connect to them, reprogram them, and have a new functional chip that does something completely different. So FPGAs can be reconfigured on the fly. They also try to predict the future deviations from normal operations, and they've taken the system and they said, here are the normal operating parameters, and if you're outside these bounds, then we're going to use prediction to say how close is the current system getting to these boundaries, and if it is, what's the model of this physical process, and let's try and kick in maybe a backup controller to restabilize the system so before they even get out of hand. So security, they protect against unsanctioned use of the network for the purposes of sending new commands or software to the PLC while reporting normal condition. Again, this was how Stutnex worked. So instead of reacting to a fault the way most systems do nowadays, they're going to protect it by preventing the fault from occurring in the first place. So if there's operators and engineers monitoring these HMIs, and all of a sudden they see the values starting to approach critical limits, they're reacting, and by the time they react, it already may be too late. The system may be already be coming into an unstable state, and any mechanism that they try to restabilize the system may be too late. So their only choice is pretty much run out of the building. So their proposed solution is active defenses that cannot be disabled by MTU commands or PLC updates. So again, what they're doing is programming the FPGA, and you cannot reconfigure it. So if you're trying to send a PCL update to change a value of a controller or an actuator, they're not going to allow that because they have, again, they're using the way to predict values and watching the system to see if this is an invalid value, and let's fall back on a backup controller. So, and this whole system is transparent to the control system designer. So if you're designing this control system, you don't have to worry about how their system is implemented. It's completely transparent to you. And they can anticipate the behavior and plant state for a short period into the future. So they're not predicting, hey, how's the system going to be in the next 10 minutes? They're using short cycles. So remember, if PLC controller is working on cycles, it's going to read the current state, react to the current state, set values to the current state, and keep looping. So that loop may be seconds or milliseconds depending on how the system's engineered. So they're going to look and say, can we predict in the next 100 milliseconds, 200 milliseconds, and see where the state is going to be, and can we react to that? So the basic design approach. They integrate with conventional model-based design flow. They synthesize and formally verify the hardware implemented functions to monitor the current and future state of physical processes. And then they switch to the stability preserving backup controller if necessary. So the conventional model-based design flow is, again, how engineers normally design these circuits and these chips and stuff like that and program them. And they just want to integrate with that process and not interfere with it. Synthesizing is how they're actually programming the FPGA. And they're using some pretty cool stuff that integrates with C, the C language, and I'll go through that in a couple slides and show you how they programmed all that stuff. So this is their design flow that they have, and this is showing the integration with current design. And the stuff that's in the darker gray box is their additional pieces that would be included in your typical design flow of a PLC. So you have your system design specifications that give you your limitations and your boundaries of how you want this controller to work. Plant modeling is how is the plant reacting to any control values that we set? How is the actuator responding and stuff like that? The controller modeling is modeling, again, the PLC in code. And this flow is showing you how they're looking at a typical flow of information through the system and where they could put their hooks in order to get their security layers to work. This is their board that they were using for their design. It's a Zinc 7000 FPGA evaluation board. So this also has an embedded ARM processor that was a static ARM processor that wasn't reprogrammable. The component that is called the Microblaze OS that they put on top of this FPGA. So again, the FPGA you could reprogram at will as long as you're physically connected to the device. This is showing the architecture, the schematic architecture of the board and the chips and stuff like that. So you can see at the lower part, this is your programmable logic part. And again, FPGAs are a really fascinating technology, and if you get an opportunity, Google it and see how that all works, and it's really neat how that works nowadays. This is their platform components. These are basically what their areas of design were for this chip. The processing system sits on the left-hand side, which is your production controller. Again, that's the ARM Cortex-A9 processor. On the right-hand side is the FPGA part, which is all, again, programmed. I'll go through each components of these and what they represent in the next slides. So the production controller runs on the Zinc 7000. They transfer the data through the I/O module, and it interacts on the AXI bus. That's how you get communication between the processor and the FPGA part. The hardware monitor backup controller is the one that's going to take a look at the system values and decide whether or not there's a backup controller kick in and stuff like that. This was programmed using C. The specification guards test the outputs for acceptable ranges of these values, and the backup controller overrides in case, again, there's attack going on and they need to. So this is the copy of the prediction unit. The prediction unit contains a copy of the production controller and plant model. It sends and receives data through the I/O module and communicates with the junction box, which you'll see on the next slide. It has 4 modes of operation: save, restore, normal, and accelerate. Save stores the current state of the plant and controller. Restore will overwrite the current state with the last saved state. Normal runs the closed loop system of the plant and controller for 1 cycle. And accelerate will run the closed loop for a predefined number of cycles. The junction box. This acts as a hub for all the 3 modules of the plant. So it's going to handle all the communications going back and forth through all these 3 modules and almost act as an orchestrator component. It manages all the flow of the control, and the timers will monitor any of the response times. And the steps that it uses in the way the program flows is a start signal is received from the junction box. The closed loop is run in the normal mode. The current state is saved. The closed loop is then run in accelerate mode, and plant and controller state before accelerator is restored. So The junction box is also going to run these watchdog timers, and if any of these timers, it's waiting for a response. If it fails or it doesn't get notified in a certain amount of time, it's going to kick in and start the reaction process. And the junction box is implemented with HDL, a hardware definition language, for simplicity. They didn't want to overcomplicate this part of the component. So the hardware monitor formal analysis, the way after they engineered everything, they wanted to prove that this system works and it's stable. So they used a language add-on for C, which is called FRAMC. And that's strictly used to formally verify functional and security specifications. It uses annotations inside your existing C code, and the C compiler will ignore it because it's embedded in comments. So the link is for FRAMC is on this slide. It's a pretty interesting technology that's used for seeing how to actually formally specify how your functions are coded. So again, the annotations will specify preconditions and postconditions of functions, your predicates, your lemmas, your axioms, and other assertions in custom logic. Formal tools are used for proofs that are taken directly from the design source code. So this Jesse is a plugin that's also part of the FRAMC that takes those annotations, and what it does is it'll generate verification conditions into the Y language. Again, if you click that link, it'll provide all the necessary information about how Jesse works and what the Y language is. And what they could do is take the output of this Y language then and then put it into automatic theorem provers that will actually validate what their functions and if they work, and with all the pre and post conditions that are there. So limitations and trade-offs of their design. So FRAMC requires manual intervention and expertise, which would require anybody that wants to use it. You're going to have to go and get trained. You're going to have to read about it, and you're going to have to actually decorate your C code with this FRAMC comments in order for it to, again, evaluate your functions. The trade-off is TESSUP is an independent, low-cost, on-chip digital logic alternative to classical mechanical interlocks used in safety systems. So they're right there on the chip. They're real time. They're live. They're monitoring your system, and they're reacting to it instantly. The mechanical interlocks, safety systems have to realize that an unsafe condition has occurred. It's going to kick in these mechanical interlocks, and that all takes time. With TESSUP, it's real time. It's monitoring it, and it's reacting right away. Plant preview is limited by hardware processing power. So if you have really intense design and plant process, you're going to need some really, strong hardware to back that up, so that this way you can process everything. And synchronization of the model in the physical plant is required. So it's going to have to keep synchronizing in order for it to understand what the system is and how it should react to it. The inability to remotely update TESSUP logic is a security asset. So that means that if somebody hacks into your network, they can't go and try and reprogram the FPGA. You actually have to be physically attached to the unit in order to reprogram the FPGA part. So again, a direct PLC access is required, which incurs higher maintenance costs. So it requires, if you need a change out for this device, you're going to have to pay somebody to go out there to physically into the plant, connect to this device, and upload the new programming changes. And then if there's outside events that are affecting the unit and stuff like that it can't really read or even monitor whatsoever, you could omit the prediction unit completely. So here they have an example of how they use the system. What they did is they used a motor controller, a simulated motor controller. Here, this is showing the code. The comment part is your FRAMC component. The behavior, that has two behaviors: verify all valid and verify any invalid. These are, the verify all valid is saying, hey, are these parameters that are mapped off of this input into the function, do they fall within the acceptable range? Verify any invalid is verifying that these parameters are now out of range. This is showing the post conditions outputs that they have with the proofs and which ones were meeting and which ones weren't. Here's a simulated attack that they ran, and the malware is going to attempt to drive the plant's output to a maximum. In figure 8, it's shown that there's no countermeasures in place, and the plant's output exceeds safety limits of 3.2 right after 350 milliseconds. It starts going off the charts now, and the attack is obviously succeeding. Figure 9 shows that they have plant behavior with and without prediction. So the hardware monitor is now in place. Prediction is shown with the blue line, and without prediction as the dashed red line. So the plant's output approaches acceptable limit after 480 milliseconds. So what this is showing is with that red line, without prediction, it goes off and then it immediately comes down because their system now is kicking in and taking over with the backup controller. Prediction on the blue line is showing you how fast it's reacting to the malware once it starts. So just a little hiccup and it continues on with normal operations. Figure 10, this illustrates the behavior of the backup controller. It shows you when it kicks in, how long it runs for, and when it turns the production controller back over to its normal operations. The predictive unit can forecast and thwart the attack again in real time. So conclusions of this paper. Existing efforts to secure systems are generic. So it's kind of like, they're going to try and genericize all the security layers and stuff on every layer of your network and the business systems and stuff like that. So they aren't really specific and geared toward any implementation to protect PLCs or anything like that. So they use rigorous verification again by using ANSI specification language constructs, and they're able to verify both hardware and software development components for this. They use non-standard uses of existing language tools, platforms, process specifications, and models. So then again, the reason why I chose this paper, it's near and dear to my heart because I work for Honeywell, and the software that I write actually monitors and sends real-time value updates to PLC components. So we leverage HVAC controllers, refrigeration controllers, and lighting and energy systems. So this paper actually kind of opened my eyes on some of the issues that we face daily with dealing with security issues, for some of our customers, and how with something like this, you could actually help secure these systems at a much lower level and don't rely on any of the actual users and what their abilities and authorizations are on the systems. So that concludes this paper presentation. Thank you.